Let's continue with the band theory. The structure of metals and covalent network solids results in every atom's orbitals being shared by the entire structure. For large number of atoms, this results in a large number of molecular orbitals. Remember this, molecular orbitals that have more or less the same energy, and we call these an energy band. And what is an energy band? Are molecular orbitals made of a lot of atoms that contains more or less the same energy. When two atomic orbitals combine, they produce both a bonding and an antibonding molecular orbital. The band of bonding molecular orbital is called the valence band, and the band of antibonding molecular orbital is called the conduction band. The conduction band is made of empty orbitals, while the valence band is are orbitals that are occupied by electrons, as you can see. At absolute zero, 0 Kelvin, all the electrons will occupy the valence band. As the temperature rises, some of the electrons may acquire enough energy to jump to the conduction band. The difference in energy between the valence band and the conduction band is called the band gap. The larger the band gap, fewer electrons there are with enough energy to make the jump. Then you can see here that in metals, they are so close so the electrons can jump. And that's why they are very good conductors. In the valence band, when they are very far from the conduction band, we have the insulators. That is when we have covalent molecular compounds. Then, in this case, they don't conduct the electricity because it's a very big gap and the electrons have not enough energy to jump to the conduction band. But what happened in the semiconductors that are the metalloids that are around the zigzag line in the periodic table between the metals and the non-metals? The semiconductors have a very small energy gap. And so, but some electrons can get the energy to jump to the conduction band and then conduct electricity in certain way. Not so good as conductor does, but conductors do, but not so bad as insulator do. Then we can say that the more electrons at any one time that a substance has in the conduction band, the better conductor of electricity it is. Here you have the metals that the conductivity of a metal decreases with the temperature, and if the band gap is small, you have the semiconductors as graphite that the conduction increases with the temperature. If the band gap is large, then no electrons will be in the conduction band at normal temperature, and the material will be an insulator. Doping semiconductor. Doping is adding impurity to the semiconductor's crystal to increase its conductivity. They can be two types: N-type, that is electron-rich impurities, or P-type semiconductors, that are electron-deficient impurity, resulting in electron holes. When a p-type semiconductor adjoins an n-type, the semiconductor is a p-n junction. Electricity can flow across the p-n junction in only one direction. Thus, we call this diode. This also allows the accumulation of electrical energy called an amplifier. Well, let's go now to sublimation and deposition. When you go from the solid to the gas, we call this process sublimation without going through the liquid state. And when you go back from gas to solid, we call this deposition. The melting point or fusion is when the solid is heated and its temperature rises and the molecules vibrate more stronger. Then, when the temperature reaches the melting point, the molecules have sufficient energy to overcome some of the attraction that hold them in a position and the solid melts. The opposite is the melting is freezing. Here we have a heating curve of a solid. For example, you go from the solid state and you begin increasing the temperature, but continues being solid until you get the melting point. At the melting point, the temperature continues constant, but the solid is converted into liquid. When you arrive at the boiling point, then the liquid is going, or when you arrive at this point, all the solid is converted into liquid, and then you are in the liquid state. The process of melting is endothermic. So delta H, the enthalpy, is always positive because it's absorbing energy, while the opposite process is exothermic. It means that it's negative. It releases energy. So the enthalpy of crystallization is equal to the enthalpy of fusion, but with the opposite sign. Generally, much less than the enthalpy of vaporization. The enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. Here you have an example and comparison of the enthalpy of fusion in blue with the enthalpy of vaporization in red for water, rubbing alcohol, acetone, diethyl ether. And here you can see the curve while we are heating the water, and it goes from the solid state to the liquid state going through the melting point, that is this temperature that remains constant while the change of state from solid to liquid. And here you continue raising the temperature of the liquid until you get the boiling point. At this point begins the change of state from liquid to gas. But during this process, the temperature remains constant until you get the change of state of all the substance. Then here the substance is in the gas state. Here you have the melting point, and here you have the boiling point. Here you have a problem of calculating the enthalpy or the energy that you need to make the change of certain amount of substance. In this case, you use the, the, the formula that the amount of heat is equal to the mass times the specific heat of a substance times delta T, that is a change of the temperature during the process. In this case, we begin heating 1 mole of ice from minus 25 Celsius degree until the melting point 0. And then, knowing the specific heat of ice, you can calculate the amount of heat that is necessary to make the change of state. Later, you go over the melting, the process of melting. That is equal, the energy in this case is equal to the number of moles times the enthalpy of fusion. The enthalpy of fusion of ice is 602 kilojoule per mole. Then you multiply 1 mole per this enthalpy and you get the amount of heat necessary to make the process of melting. In order to heat 1 mole of water, liquid water, from 0 to the boiling point, that is 100 Celsius degree, you use this formula and you can calculate using that the specific heat of water is 1, is 1, then you can calculate the amount of heat, uh, well, the specific heat of water is 4.18 joule per grams per Celsius degree. Then you know that 1 mole of water is 18 grams. Then using this formula, you can calculate the amount of heat that is necessary to make the change. And here you have the same process for the boiling point and the process for heating the vapor until 100 Celsius degree to 125 Celsius degree. The sum of all the amount of heat that are necessary from here to here is it can be calculated by adding all this amount of heat in every step. Here you have a curve where you can see the phase diagram where you have the solid, the liquid, and the gas. The line that divides the solid uh, from the liquid is called the fusion curve. In this diagram, you have the temperature in the X, and in the Y you have the pressure. So you have here that the curve, a sublimation curve, is between the solid and the gas. And the curve that divides the liquid from the gas is the vaporization curve. These three